So welcome back to the session. We will see about the next topic. See, in the last topic we study about the elements of optical communication system, and now we discuss about the next topic. That is about the advantages. Excuse me. If you see the advantages, what is the first advantage? High bandwidth, high bit rates will be passed, high speed, no corrosion. If you see the copper cables, we can have a problem called as corrosion problem. But when you see about the same thing with this optical fiber cable, there is no corrosion for the OFC, optical fiber cables. There is no corrosion is present. And fifth point, when you see about the advantages, weight is less, your weight is less. And sixth one is, if you talk about the optical fiber cables, the sixth point that we can see is size of the fiber is small, size of the fiber is less, size of the fiber is less. So, these all are the advantages we are having when we compare that with respect to the OFC, optical fiber cables. So, there are some other advantages are also there, we can see them, such as if you talk about the first advantage, that is called as raw material, which is called as abundant raw material. So, we are having abundant raw material is present. So, next one is eighth one. Why abundant raw material? Because we can use silica. Silica is nothing but a sand. From sand we are getting the glass where we can have abundant raw material. But copper is one of the metal which we need to find out, extract from the ground and try to make the copper cables. But for silica it's an sand we are having, abundant raw material is there. But for using the continuously about the your what is called as copper metal, then what happened means after some days we are having a deficiency about the mineral, that about that metal, we are not able to available, that in abundant raw material cannot be available with respect to the copper. But for glass we can manufacture with silica, so much we are having abundant raw material is present, okay, and reliability is also very high, reliability is very high, okay. I will write one point here instead of writing it another point as high speed and security is also very high, security is also very high. So, what about this security I will explain to you, like in 2 words I will explain simply to understand the security, okay. So, what is that security in the sense means, first point is, whenever the copper wire is going, we cut the copper wire and connect the telephone to that one, we can make a calls to this one by using that copper wire. So, whenever a copper wire is passing through your window, you can cut that copper wire and you are going to be connected your telephone to that one and try to make a call. So, we can it is possible for us to make a calls security wise, but it is not possible with the copper wire, with the coaxial wire. If you cut the coaxial wire, it is not like taking another coaxial wire and making to twist like this, you get some powder wire at the glass powder. That means it is not possible to connect like this. A specialized training is required to make a splicing, and even a splicer also required, splicing machine is also required. So, that is the point, security point of view, it is going to be very, very high, and moreover it is very much immune to interference. So, immunity of interference is also very, very high, the second point I will tell to you. So, how security, It is immunity to interference also. So there is no chance of having interference. What's the meaning of interference means? Just try to understand. When two signals are having same frequencies, are mixing with each other, is called interference. Is called interference. But yeah, noise is different, distortion is different, interference is different. As a electronics and communication engineering student, you must definitely know about the difference between these three: distortion, interference and noise. Okay, so these three are going to be very, very important. So I explained to you about the interference. Interference is nothing but a mixing of two signals with same frequency is called as interference. Distortion is nothing but a change in the waveform, shape of the waveform is called as distortion. Noise is nothing but any unwanted signal other than the required signal is called as noise. Sorry, any unwanted signal other than the required signal is called as noise we are having. So please put this into the mind such that these three are completely different. Bhaiya, many students will have a doubt such that what is interference, what is noise and what is distortion. Okay. So two signals of different frequencies are mixing with each other, that is noise. Two signals of same frequency is mixing with each other is called as interference. I hope it's clear. Now I can go explain you about the disadvantages. So students, we will see about the disadvantages. What are the disadvantages that we can have? So can you please tell me what is the first disadvantage we are having? The first disadvantage that we can see in here is, it is nothing but an, okay, cost is very, very high. Yes or no? Cost is high. So we are going to be using for long distance, more distance we are using. If you are using for more distance, we need to include more number of repeaters. As usual, more number of repeaters, and manufacturing of fiber is also a very costly affair. That's why the cost is very, very high. So after that the cost, we can see about the next important one, that is called as, so equipment is required, special equipment is required, special training is required. So we can tell that special equipment is required, special training is required. So these two are very much important whenever we are discussing about the disadvantages. So first one is the cost is high. The second one is we can tell that equipment is required, that is special training and equipment is required. So we can tell like this: special training and equipment is required. Special training and equipment, special equipment and equipment is required. So without this we can't do anything, bhaiya. So as an engineer, we cannot do the splicing directly, and it's not our task also. The diploma student can do the splicing. As an engineer, we design the fiber, that's it. And we the engineers are never go for any splicing or like this. And of course, if it demands, we can do it because we know splicing how to do it also. So that's what we can have a special training and equipment is required for doing that splicing thing, or repairing or maintaining a connection, or knowing about the signal strength is present toward the line or not. All those things we have equipment are there. As an engineer, we design those things and we can use those things. The diploma students will going to be definitely use those things in the field work. Okay, so that is completely what happening. Special training and equipment is required. After the next disadvantage, we can tell that the strength is less. The fiber cables are having less strength. I think you understand this. If you take one copper wire and if you take one fiber cable, then definitely the strength of the copper wire is going to be high. Why? Because means if you bend the copper wire also, there is no problem with the copper wire. It can bend as per your convenient. It is to be bend. Like sharp 180 degrees, 90 degrees also it can bend. 180 degrees also it maintains. But if you see about the same optical fiber cable, if you bend it 180 degrees, glass it is manufactured which is brittle in nature, it can definitely break down. And the light cannot be passed from one end to the another end if you bend it. So that's why the strength of the optical fiber cable is very, very less. So strength wise it is going to be very less. And the last important point, remote power supply is required. Remote power supply is required. If you talk about the remote power supply is required. So what is this remote power supply is required? Just observe this diagram, you will get a clarity regarding that. भैया हमारा डायग्राम में एलिमेंट्स ऑफ ऑप्टिकल कम्युनिकेशन सिस्टम में रिपीटर है. This repeater is not optical device. It's which device? Electronic device. Because of that electronic device, it has to be run. It requires some supply. Some power is required for that one. That power is going to be maintained along with your optical fiber cable. You are also going to be sending one power cable, and that power cable will going to be carries this power. Carry that power, and that power will going to be make this device to work. That means the remote power supply is always required. If you are making it within the ground for long kilometers, for so many number of kilometers, assume from Delhi to Pune, you are making a connection between that. So we have to maintain a power cord cable also along with the optical fiber cable to make it repeaters to be work. That's what the main important thing. Remote power supply is required. So it is completely about the optical fiber cable disadvantages we are having. So next one is, we will see about the applications. So you can please copy this part. I can tell the applications to you. So orally I can explain, and I can explain the points to you. We can use in the military, we can use in the civil applications, we use in telecommunication systems, fiber optical cables, in cellular. Telecommunication means everything via cellular, landline, whatever it may be. So we use in public networks, PN, use in public networks, in civil, in industrial applications we use, in sensor, optical sensor applications we use, and moreover thing that we can use other than the communication, military, scientific and research applications also we will use it, right? Like computer networks, in LAN, in computer networks also we will use the optical fiber cable, in computer applications. So this is about the applications. So I explain you about the 5 applications to you. First one is use in public networks, okay, use in telecommunications, use in military, use in civil and industrial applications, used in LAN, in computer network applications, and also it is used in computer applications also. So this is a completely, we are having some 6 applications or 5 applications we have, all are very important about the optical communication system. So this is completely introduction guys we are having. So we can write those points also here. So writing as application also I can explain those points, writing as applications. So we can note down the first thing, application used in the public network. Bhaiya, these are used in the public networks, also called as public network, public networks, which is called as switching networks also we use, like telecommunication we use, means they are called as public switching networks we are having. So we are using the telecommunication, we use in telecommunication, used in telecommunications. We use this in military applications. In military, they use the separate cables can be used for the military applications. Fourth one, they are going to be used in the civil and industrial applications. So used in the civil and industrial applications we are having. Fifth one is nothing but we can call it as the fifth application, where we can use it for our LAN. LAN stands for the local area network, LAN, LAN, local area network, used in computer networks bhaiya. So sixth one we can use for the computer applications also. So we use for the computer applications. So this is what said to be called as the, for computer applications we are using this part. So it is completely what we said to be called as the advantages, disadvantages and applications we are having. So we will study in our classroom about all these applications bhaiya. Other than these two, like military and civil applications are not studied by us in the classroom. And please write down this also, very much important. I will just give an example for this one, which is called as optical sensor applications. Optical sensor applications. So optical sensor application we are having, like sensors are there, optical sensors are there. Like simply example is barcode. If you are QR code scanning bhaiya, if you go to the your so called in the market, you can purchase some products in the grocery market, and that you are getting scanned. So one simple example to understand where the optical scanner is used to know about the reflective principle mechanism to get back the output, okay, about the product information. Hope you understand. So please, these are the advantages, disadvantages and applications, right? Please copy it. right. So this is completely about the introduction topic. So now I am explaining you about the next one, which is called as next topic, the review of optics. I hope you see the syllabus in that I told you such that the second topic is called as review of optics. Review of optics, I will just explain to you. So some of the basic concepts that are most important for us for knowing about how light is passing into a fiber. Yeah, please know this part, guys, all of you. Review of optics, the first one is called as nature of light, which is called as nature of light we are having. So bhaiya, a light will always having a dual nature. It is always having a dual nature. The first one is called as your wave nature. First nature is called as wave nature, and the second one is called as particle nature. Second one is called as particle nature. So if you talk about the wave nature, this nature was going to be proposed by the Maxwell, and he gives that velocity of light c is equal to 1 divided by root of epsilon naught into mu naught, where epsilon naught is called as the permittivity of free space and mu naught is called as the permeability of the free space. And such velocity of light, by putting the constant values of this, it is equal to 3 into 10 to the power of 8 meters per second, which is called as a wave nature. So whenever the light was passing from one point to the another point, it is going to be always satisfies the wave nature. It have incidence, refraction as well as reflection. It is present. So when you talk about the particle nature, this particle nature was proposed by the Einstein and Planck. So two great scientists, Einstein and Planck. So particle nature is mostly used whenever the light was absorbing and on any of the devices absorbing, the particle nature comes into the picture. So when the light will come and falls on the any of the material or any of the type of a compound, then we can know such that the particle nature is used. If you talk about the particle nature, it is nothing but an energy present in the photon, that is EP. P stands for photon. Nana. Photon is nothing but a packet of light energy is called as photon. A packet of heat energy is called as phonon. The amount of energy that present in a photon is directly proportional to the frequency. That is, EP is directly proportional to the frequency we are having. So EP is directly proportional to the frequency. Energy present in the photon is directly proportional to the frequency we have, which is called as the operating frequency we have, is called particle nature is present. So that is replacing with a constant called as Planck's constant, which is given as h. So h into f. So the equality comes into the picture, we are putting a constant. So h is called as Planck's constant we are having. So when you talk about the Planck constant, it is very clear such that it was removing your directly proportionality and gives you the Planck's constant, and such Planck's constant is 6.626 into 10 to the power of minus 34 joules per second, and h is called Planck's constant, f is called operating frequency, EP is called as energy present in the photon, which is given as joule. So bhaiya, and we know that h is equal to Planck's constant. I am writing here, it's a Planck's constant we have, so given by the Planck. So h is equal to 6.626 into 10 to the power of minus 34 joule second. So observe very clearly, guys, if you talk about the joule second and this frequency is equal to 1 by second, cancelled out, second cancelled out, energy EP is in terms of joule. So it is proposed by the Planck and Einstein, which is called as the particle nature we are having. So what can we understand from this nature, dual nature is, when light traveling from one point to another point, it is in the free space, it is acts as a your wave nature. In the guided medium also it acts as a wave nature. But whenever the light is falling on any of the material, then it is going to be absorbing the light, okay, or it is reflecting the light, and all those things are depending upon the particle nature. Depending on the particle nature, energy present in that photon will going to be decides that. Now please see here, Bhaiya, I will tell one more point also. EP, if you observe carefully, EP is energy present in the photon. H is Planck's constant. H into, already I told you in the classroom, F and the relation between lambda. So lambda is equal to C by F, then F is also equal to C by lambda. So replacing your F with C by lambda. Then we got that energy present in the photon EP is equal to H is Planck's constant and C is also a constant, 3 into 10 to the power of 8 meters per second. Do you observe one thing carefully such that this one is going to be present as 1.24 divided by lambda, and we can write this in terms of the value like this. So before writing directly the formula, I can explain directly instead of writing this part. Now see here, that is given as lambda. Lambda is equal to H into C divided by EP. So when you take your energy present in the photon in terms of electron volts, EV, in terms of electron volts, then this become 1.24 micrometers. That is the wavelength. Relation between the lambda wavelength with respect to energy present in the photon is given like this. So lambda is equal to 1.24 divided by EP into electron volts, which is given as micrometers is present. I hope so everybody in the class understood this. The first topic, review of optics, is nature of light. We study all these topics, review of optics topics, all these topics in the physics also, which is given as nature of light. Please note down the point, all of you. Vishwa Trivedi, yes, some of the topics of this subject will also be covered in the GS also. In information technology, we can get some of the topics of this subject will also be covered in GS, like mostly data communication. Aditya, you can take second edition of all the books. I think there are still third edition is also there, and for Van Tomasi book, go for 6th edition. For Van Tomasi 6th edition, and for Behrouz Forojan also, I think it's 4th edition is required. Behrouz Forojan you want 4th edition, Van Tomasi 6th edition. So remaining all are second editions is sufficient. There is no much changes after that. Second editions, all the time you can follow the new editions only. Okay. Yeah, copying is completed means please put a message. Okay. So the next topic is optical power. I think copying is completed. So next topic is optical power. Optical power is also called as the radiant flux. It is also called as radiant flux, which is represented as phi. Optical power represented as P. Optical power P is equal to dq by dt, rate of change of optical energy. Rate of change of optical energy is called as optical power we are having. Okay. So, the rate at which electromagnetic wave transfer light energy is called as optical power. So, P is equal to dq by dt, we have the formula. You can also write it in terms of radiant flux also, which is called as phi. Bhaiya, please concentrate on two important points. Radiometry. Radiometry is nothing but it deals with the completely all optical frequencies, means 10 power 12 to 10 power 16 hertz. Photometry. Photometry is nothing but it's a science which deals with only visible light, only deals with visible light frequencies. If you are dealing only with the visible light frequencies, that is called as photometry. If you are dealing with all the light frequencies, it is called as radiometry. That means we are talking about the IR. IR frequencies we are studying in the classroom. IR is in the range of the optical frequencies, not in the visible range. Okay, then what we have to consider is it's called as radiometry. The radiometry means the power at that radiometry frequency is called as radiant flux. It's called radiant flux phi, it is called as. I hope everybody got this one. So, P is equal to dq by dt, optical power P. So, rate of change of optical energy is called as your optical power. Obviously, you know power is equal to energy by time. So, what we studied in our basics parts of our signals and system also, when energy and power signal, we know about power is equal to energy upon time, total energy by total time also we can consider it. So, P is equal to E by T, that is why we can consider the total time all the time, energy 1 by 2T will come by in the formula also. Hope it is clear. Yeah. Now, see here, P is equal to dq by dt, that is called optical power P, radiant flux is called as phi we are having. It is measured in, please concentrate, it is measured in dBm. dBm stands for the millimetric, decibel millimetric, okay, or decibel milli, which is called as dBm, or dB mu, decibel micro, okay, micro decibels, milli-decibels is called as dBm or dB mu we are having, okay, which is given as reference as milliwatts, reference as microwatts, it is called as reference of milliwatts, it is microwatts. So, reference of microwatts we are having, which is called as microwatts is present. This is what said to be called as optical power we are having. So, please see here, power P is writing in terms of dB, Nana. Just try to understand. If you want to write our power in terms of dB, we have to apply 10 into logarithmic of power P divided by reference is 1 watt by a of base 10, which is called as dBW or simply called as dB. dB watt or dB. dB stands for the decibels. What is the use of writing this decibel? Okay, why you are writing in terms of dBm and dB mu? Why generally we use in decibels is very simple. Whenever the quantity is having very small value is present, writing in terms of decibels will show you very clearly such that some amount of real number will come. For example, we are having a value of 2000, we are having a large quantity or small quantity is present. If large quantity is there, for example 2000 is there, if you write 10,000 is there, if you write in terms of decibels, okay, it is going to be getting equal to that of 10 to the power of 4 dB we will get now. So, what it indicates, sorry, it is called 40 dB we will get. What it indicates clearly is, it is nothing but an, you are having very small unit, see very 10,000, very 40 dB. So, writing in a small number, that is what called as decibel importance. So, writing in a small number is called as the decibel, it is called as dB, decibel we are having. Now, just try to understand the concept by we know that whenever the frequency is very, very high, the amount of power present is very, very low. That is what entirely we studied in our concept called as signals and system given by the Fourier series and Fourier transform, we studied the same thing by As long as the frequency is very, very high, the amount of power present is very, very less. Why? Because means the higher frequency components are having always the less power we are having. That's the phenomena, that's the natural phenomena, there is no doubt about that, no need to change that also, even though it is to be proved by the Fourier also. Okay, so frequency is very high, amount of power present is very less. Because frequency is high, the magnitudes become less, the amount of energy or power present is very less. That's the reason most of the energy or power is always concentrated at the low frequency. At low frequencies, we have most of the energy and most of the power is present. I hope everybody in the class understood this point, right? So I am not making any confusion for you. Already we studied that in our topics of signals and system, even though we study the same thing in communications also. So if you talk about the point here, my power is very less. Obviously you know that. Why? Because means our frequency is very high. If the power is very less, then we are taking the reference with respect to milli and with reference with respect to micro. Reference with respect to milli and reference with respect to micro, what happens is the amount of power that we are getting is going to be in a sustainable dB value will be obtained. That's written as dBm and dB mu is written. Okay. For example, if I write 0.00001 watt is present, assume that the amount of power present. As an example, there is no rule such that like this only power has to be present. Assume that power is 0.0001 watt is present. So when power is 0.001 watt is present, I will write the power is equal to 1 into 10 to the power of minus 3. Okay. So that is, sorry, minus 4 it is present. So 10 into the value is equal to 10 to the power of minus 4 we are having, is equal to minus 4. So we write that value is equal to 10 to the power of minus 4 is present. So this value P is equal to 1 and 10 to the power of minus 4. Now if you write the same thing in terms of dB, that is decibels, see P is equal to 10 into log of 1 into 10 to the power of minus 4 dB. This minus 4 will come here, that is equal to minus 40 dB is present. Okay. But if you write the same thing, power in terms of dBm, see now reference is with respect to 1 milliwatt. By 10 into log of 1 into 10 to the power of minus 4 divided by 1 into 10 to the power of minus 3, reference is with respect to milli, this will cancel out. We get only 0.1 is present, that is minus 10 dB we are getting, minus 10 dB we are getting. So this is what the reference, how you write it in terms of dBm. So writing in terms of dBm, see power in present of dBm, so optical power, not only optical power bhaiya, in advanced communication system when you are operating at high frequencies, gigahertz, terahertz, we always take in terms of dBm or dB mu. Okay, sometimes you will take dB also, so dBm we are taking. Now the simple thing, see dBW means reference is 1 watt, that is power P divided by 1 into 10 to the power of minus 3 of base 10, which is called as dBm we are having. So whenever we are talking about the power that is equal to dB mu bhaiya, it is called as dB mu. If you talk about the dB mu, that is equal to that of 10 into log of power P, because dB mu, the reference is with respect to micro, so 10 to the power of minus 6, which is called as dB mu of base 10. So higher the values, we have to make it a very small value of dB also, reference is taken with respect to dBm and dB mu. Okay. So this example only for clarification purpose, not write in the notes, only to understand this part. Okay, I explain the entire thing to make it clear to understand what is present there, right. Now just observe here, I will tell one thing, please concentrate. dB plus or minus dB is equal to dB, and it is the same thing, dB that is equal to dBm plus or minus dB is also equal to dBm only, because log of this by log of this we are going to be considered it. So because log A by log B, because dBm minus dB, log A minus log B is equal to log of A by B. So log of A by B in the sense means that is going to present as dBm only, So that is the thing we are having. When would I write this bhaiya? dBm minus dBm is equal to dB, By log A minus log B, that is equal to log of A by B, milli cancel, left over with only dB. That's for the reason. That's called dB we are having. So I hope everybody in the class understood this, what is called as optical power. You please note on this, I will tell a point as a note to you, like 2 points I will explain to you. Please copy it, Nana, all of you. Kushbu, particle nature is nothing but whenever the light is falling on any of the material, then the amount of energy that can be absorbed by that particular material can be obtained with the help of a particle nature. Like whenever the light will come and falls on a photodetector, then we can deal with particle nature. Okay, so that means the amount of energy that present in the photon is directly proportional to the frequency, operating frequency, or at what frequency the light is present. Okay. Higher the frequencies, higher the energy present in the photon. Yeah, clear? If copying is done, please put a message, Nana. I will explain some points. If copying is done, just please put a message, I will explain some points to you. Right. Please write on the first point. The optical power measures the rate at which electromagnetic wave the optical power measures the rate at which electromagnetic wave transfers light energy. Electromagnetic wave transfers light energy. Next point. Optical power is generally stated in dB. Optical power is generally stated in dB. Relative to the defined power level, stated in dB, relative to the defined power level relative to the defined power level such as 1 milliwatt, such as 1 milliwatt, 1 milliwatt or 1 microwatt or 1 microwatt, such as 1 milliwatt or 1 microwatt or 1 microwatt. Okay, right. So we will see about the next topic. We will see about the next topic. Put the heading as refractive index. Refractive index N. Next topic is refractive index N. So we are discussing about the next topic, which is called as refractive index. Refractive index N is equal to velocity of light in vacuum to that of velocity of light in medium, C divided by V. C is nothing but an velocity of light in vacuum and V is nothing but an velocity of light in medium. So refractive index is defined as the ratio of velocity of light in vacuum to that of velocity of light in medium, velocity of light in medium. So which is given as N is equal to C by V. We can like this also, N with respect to your relative permittivity, epsilon r, under the root of epsilon r. Okay, root of epsilon r with respect to the relative permittivity we can write. If you talk about the velocity of light in vacuum, if you see that in vacuum, refractive index, so velocity of light in vacuum means right now your medium is vacuum. So medium is vacuum means velocity of light in vacuum, velocity of light in vacuum, both vacuum will get cancelled out, then velocity of light N is equal to 1. N is equal to 1. So from this what you understand is your refractive index N should always be greater than or equal to 1. N should be always greater than or equal to 1. Why? Because there is no other alternate. Why? The reason is such that medium and vacuum are becoming same only equal to 1. So starts at 1, equal to 1 or greater than 1 we are having. If your medium is air, it's not vacuum, if your medium is air, N is equal to 1.0003 we are having. Okay. So 1.0003 we are having. So that is equal to that of your value equal to 1 only we will consider it. That is why in some books you will write directly velocity of light in air and velocity of light in vacuum both are same equal to 1 only. That is true. The reason is N is equal to 1.00003. No need to consider that, you can just remove it and write it value of N is equal to directly equal to 1. Next, if you talk about the water via, velocity of light in water is 1.33. These are fixed values. They measured it and they are giving it. Facts. We can call them as facts. So it's water. Next, ethyl alcohol, which is called as ethyl alcohol we are having. When you talk about ethyl alcohol, N is equal to 1.36. Okay, don't mix water and alcohol by they are different. Water refractive index N is 1.33 and ethyl alcohol is N is equal to 1.36 we are having. So next one is called as fused quartz. It is called fused quartz we are having. The fused quartz is also one type of material whose refractive index value N is equal to 1.46 we are having. Okay. So N is equal to 1.46 is present. Next one is glass. The refractive index of N is equal to 1.5. It varies from 1.5 to 1.9 by year. In between 1.5 to 1.9 the refractive index is present for glass. But we can take it is equal to N is equal to 1.5 most of the times. So, value of n is equal to 1.5 we are taking. Okay. So, next one we can tell about the refractive index, that is given as for diamond. For diamond, the refractive index is a high value, that is n value is equal to 2.42, and for silicon the refractive index value n is equal to 3.2. Okay, n is equal to that of 3.2 we are having. So, this value of n is equal to 3.2 we have. So, just observe it, that value is equal to 3.2 for silicon. So, I hope everybody in the class will understood this. So, these all are the refractive indices we are having for different materials. So, next point I want to explain to you with respect to the refractive index is, when the light was moving from one medium to another medium, it changed its wavelength rather than the frequency. Frequency remains the same, but it changes the wavelength. Now, just observe it. So, light moving from one medium to another medium, it changes its wavelength rather than the frequency. Frequency remains the same for the light ray, but it changes the wavelength. Wavelength is changing from moving from one material or one medium to another medium, or one material to another material. Now, after writing this part, I will explain like this. We know that lambda is equal to C by F. So, we are writing that lambda naught is equal to C by F naught. So, C is equal to lambda naught into F naught, So, lambda naught into F naught. So, we can write like this by that is called as lambda is equal to V by F, general case we are writing. Your V is equal to lambda into F is present, that is equal to V is equal to lambda into F we are having. Now, why? Because I am writing this one means, whenever we know such that your frequency is changing, your light ray is changing from one medium to another medium, your frequency remains the same. So, here F naught is equal to F we are having, your F naught is equal to F is present. So, there is no change in the frequency, frequency remains the same. For the refractive index, n is equal to C by V. But C is equal to lambda naught into F naught, and V is equal to lambda into F. F naught and F both will get cancelled out, and n is equal to lambda naught by lambda. This is another formula. So, totally I gave three formulas for refractive index. N is equal to C by V, first one, n is equal to root of epsilon r. I am not explaining how you get root of epsilon r. The reason is already we studied in the EMTL. That's why I am not talking about that part. And the next one is your n is equal to lambda naught by lambda, where lambda naught is the free space wavelength and lambda is the wavelength that is present within the medium. So, it is completely about your refractive index. I hope everybody in the class understood this. You please copy this. I will tell the points regarding this refractive index. Bhaiya, please copy this part. Vishwa Trivedi, it is not EM wave transverse, it is transfer. which electromagnetic wave transfer light energy, not transverse. Transverse is different, transfer is different. Transfer, please correct it. In optical communication, we use both particle nature as well as wave nature also. Wave nature is uses about the light is emitting or light is absorbing by the any material. We can use the particle nature. We use the wave nature whenever the light is traveling from one point to the another point, is called as wave nature we considered, proposed by the Maxwell, where it considered to be as a electromagnetic wave having your electric and magnetic fields in quadrature to each other. That is, your electric field and magnetic fields are quadrature to each other, and that is what called as your wave nature. It is not transverse, it is simply transfer. Electromagnetic wave transfer light energy. Electromagnetic wave transfer light energy. Yeah, right on the first point, note in refractive index, all of you. First point, note refractive index. Refractive index is the ratio of velocity of light. Refractive index is the ratio of velocity of light. Is the ratio of velocity of light propagating in free space. Velocity of light propagating in free space to the velocity of light propagating in the given medium or material. In the given medium or material. In the given medium or material. Okay, right. Next point. Right. The more dense the material, the more dense the material, the more dense the material, the slower the speed of the light, the slower the speed of the light, the slower the speed of the light in that material, so n is greater than 1 for all materials. So n is greater than 1 for all materials. So n is greater than 1 for all materials. Greater than 1 for all materials. Right. Next point. The frequency of light does not changes. The frequency of light does not changes. When it passes from, does not changes when it passes from one medium to another, when it passes from one medium to another, but the wavelength must change. But the wavelength must change. But the wavelength must change. Okay, right. See here. Next topic, Snell's law. So we are discussing about the Snell's law. Snell's law. Snell's law provides the angle of refraction it provides the angle of refraction. Angle of refraction, that angle of refraction is called as theta 2. Now just observe it, all of you carefully. This is the boundary of the material. So boundary between the two materials, just listen. This is called as medium 1 and it is said to be called as medium 2. Medium 1 is having refractive index N1, medium 2 is having refractive index N2. The refractive index of medium 1 and medium 2 are not same, they are different. So whenever we talk about that two mediums, that is two materials are there, two different materials called as two mediums. This is medium 1 bhaiya and this is medium 2 bhaiya. Light is travelling from medium 1 to medium 2. Dekho bhaiya. Light is travelling, see I am talking about the light which is travelling. It hits the boundary. The point at which the incident ray hits the boundary, a line drawn perpendicular to that point of incidence of the incidence ray on the boundary is called as normal. I am explaining once again guys. Please concentrate करो भैया. ये incident ray है which is called as incident ray we are having. It is the incident ray. So when the incident ray is moving from medium 1 to medium 2, it hits at the boundary or hits on the boundary. A line drawn perpendicularly at the point of that intersection of the boundary is called as normal. I hope everybody in the class understood this. Dekho bhaiya, please see the case, that is incident ray. The angle that maintained by the incidence ray with respect to the normal is called as theta 1. Theta 1 is called as angle of incidence. Theta 1 is called as angle of incidence. Incidence ray is the light ray which is going to be moving from medium 1 to medium 2 through the boundary. At the point of intersection of the boundary, we are going to be drawing a line perpendicular is called as the normal. I hope everybody in this class understood this. Dekho bhaiya, right? Please see the white color only. I will change the color for the next case. Talking about the case 1. Whenever the refractive index of material of medium 1 and medium 2 are same, the meaning of that one is N1 and N2 are same, the light will travels into the another medium without having any deflection. N1 is equal to N2. At this instance, your theta 2 is also equal to theta 1. Your theta 2 value is equal to theta 1. This is what the line we are going to be drawing is called as theta 2. Bhaiya, theta 2 is called as angle of refraction and this ray is called as refracted ray. It is called as refracted ray. I hope everybody in the class understood this one, case 1, N1 is equal to N2. The light ray will incidence from medium 1 to medium 2 will travels within the straight line without having any deflection equal to theta 2 is equal to theta 1 when N1 is equal to N2. Okay, right. Now talking about the next one, that is explaining about the case 2. When it is moving from denser to the rarer medium. So I can use another color pen to make it clear. I am taking yellow color bhaiya. So light was moving from denser to rarer medium. It will move away from the normal. The same refracted ray, it is moving away from the normal and the angle it maintains is called as theta 2. So what is the condition here, theta 2, and this is given as like this, your N1 is greater than N2. Obviously your theta 2 is also greater than theta 1. See, observe here, theta 2 is greater than theta 1 bhaiya. Dekho, yellow color line. Theta 2 angle is very much higher when compared to theta 1. So what we understand here is your theta 2 is greater than theta 1 we are having, then n1 is greater than n2. The light was moving from denser to rarer medium, case 2 bhaiya. Denser to rarer medium. So denser to rarer medium means n1 is higher, n2 is lesser. That's what written in the condition. n1 is greater than n2. So what's the result you observed here clearly is from this white color line and from this yellow color line is that is the light ray, reflected ray is moving away from the normal. It is moving away from the normal bhaiya. So that is called as moving away from the normal. It is called as away from normal. I hope everybody in the class understood this. It is called away from the normal. This is the case 2. Now I am explaining with the case 3 bhaiya. So I am taking another color, that is the green color. Hope it's clear for you. Talking about the case 3, leftover case is moving from rarer to the denser medium. So whenever the light was moving from rarer to the denser medium, देखो भैया rarer medium to denser medium चल जाएंगे. So then we observed clearly like this, that is called as your n1 is less than n2, then the resultant theta 2 is also less than theta 1. This is equal to theta 2, the theta 2 is less than theta 1. When this condition is happening, it is happening whenever the light is moving from rarer to denser medium. So what is the effect you observed when the light is moving from rarer to denser medium? It is moving close to the normal, which is also given as in a good English, it's called as towards the normal. So it is moving towards the normal bhaiya. So towards the normal we are having. So you observe the cases, the 3 cases bhaiya. Case number 1, n1 is equal to n2, both the 2 mediums are same, theta 2 is equal to theta 1. When n1 is greater than n2, theta 2 is greater than theta 1, moving away from the normal when the light is passing from denser to rarer medium. Coming to the case 3 bhaiya, whenever the light is moving from rarer to denser medium, your n1 is less than n2, obviously theta 2 is less than theta 1 and light is moving towards the normal. I hope you understand all the things about this one. So I am applying a Snell's law. So telling directly, this is the point which we call it as A. Okay, at A. So applying Snell's law at A. So writing here, apply Snell's law at A. So we are applying the Snell's law at A. So now what we are telling here is, it's very clear, that is, so when I write about the apply Snell's law at A, we can tell Snell's law gives the relation between refractive index and the angle. What is the refractive index of this medium? n1, very good, n1. So what is the angle here? Theta 1. So n1 into sin theta 1. See, at A, the angle we are having is sin theta 1 and n1 into sin theta 1. Right. If you are going to make this as a components like medium, and of course the derivation is there, not required for us, I am just giving a relation. So that is called as n1 into sin theta 1. So n1 into sin theta 1 we are having. So is equal to, see, coming to the another medium, what is the refractive index of another medium? n2 bhaiya. n2 is the refractive index of another medium and what is the angle maintained by this one? Theta 2 bhaiya. So उसको बीच में relation में n2 sin theta 2. Just observe one point clearly, you will get like this, sin theta 1 upon sin theta 2 is equal to n2 by n1. This is what called as Snell's law. We can find the theta 2. Okay, we can find the theta 2. So this is what said to be called as the Snell's law we are having. We can find the theta 2 from that relation if you know n2 and n1 and the theta 1 angle of incidence. I hope everybody in the class understood this. You please copy, Nana, please copy. Sagar, n1 n2 kaisa compare karne means it's very simple. Assume that your light is moving from n1 as air into water n2. then you definitely see the bending phenomena in the light, which we call it as refraction, and that bending phenomena was going to be done towards the normal. If you take a glass of water and put a straw into that glass of water and you observe from the other side, you can find out that the straw is bending in the glass. That bending phenomena of the straw was said to be called as simply it is coming close to the normal, okay, because it is passing from N1 to N2. Same thing, bhaiya. Complete now copying. Right. See, for example, this is water and this is air. Assume refractive index of water is N 1.33. N is equal to 1.33. Refractive index of air, N is equal to how much? It is 1. So, what you understand here clearly is, it is what said to be called as light is now moving from which medium to which medium? Denser to rarer. Denser to rarer medium, bhaiya. Okay, then light will move away from the normal. Away from the normal in the sense means it comes to this part. Clear na? Okay. So, this is what said to be called as Snell's law we are having. So, which is called provides the angle of refraction. Okay. Snell's law provides the angle of refraction. Right. So, please see here the next topic I am telling to you is called as critical angle. Critical angle, bhaiya. So, next topic is critical angle. Your critical angle is represented as theta c. It is called theta c. Your theta 1 is equal to theta c if theta 2 is equal to 90 degrees or greater than 90. That angle is called critical angle. At that critical angle, what happens is the light ray is going to be passed like this. Once again, please follow here, bhaiya. It is a boundary between the two materials. So, we are having N1 and it is called N2. Light is incident. Line drawn perpendicularly at the point of intersection is called as your normal. It is called as your normal we are having, and this is what the angle of incidence said to be called as theta 1 we are having, and it is said to be called as normal we have. It is called as normal. And here the angle what you are going to be considered is said to be called as theta 2 is equal to 90 degrees. Then the light ray was going to be passes along this boundary, which is said to be called as critical angle. It is called critical angle. So, it is the minimum angle, it is the minimum angle that which we are having the light ray which can be reflected back along the interface is called as a critical angle we are having, critical angle. Okay. explain that point as a note to you. So please see here carefully. Next important one I will tell to you. From Snell's law, see already we studied. From Snell's law, what we studied? Sin theta 1 upon sin theta 2 is equal to n2 by n1. भैया as per the condition I am replacing the theta 1 with theta c. भैया देखो इधर देखो भैया theta 1 को theta c से replace किया. When this replacement of theta 1 with theta c will be happen, इसी के लिए theta 2 का 90 डिग्री सेने को तक हो जाएंगे. So sin of 90 degrees, theta 2 का प्लेस में 90 डालो, 90 डिग्री हो जाएंगे. So that is equal to n2 by n1 we are having. Sin 90 1. Then therefore it is equal to sin theta c. Sin theta c is equal to n2 by n1. So theta c is equal to that of sin inverse of n2 by n1 we are having. So this is what said to be called as your theta c, which is called as critical angle. The critical angle is equal to sin inverse of n2 by n1. Or we can tell sin theta c is equal to n2 by n1, which is called critical angle. So I can explain a point here as a note to you. You please copy this part, and after completion of your copying, just put a message. Okay. Write down the point. Keshav, thank you for the message. Write down the point. Critical angle is defined as the minimum angle of incidence, defined as the minimum angle of incidence at which a light ray may strike the interface of two medium, and result in an angle of refraction of 90 degrees or greater. Angle of refraction of 90 degrees or greater. Of 90 degrees or greater. 90 degrees or greater. Okay. Put the heading as total internal reflection. The last topic for the today's class. Total internal reflection. Total internal reflection. Right. देखो भैया, total internal reflection TIR. TIR. The name itself suggests something. Whatever the light it is passing get reflecting back. It is not passing to the another boundary. Yes or no? It's not passing to the another medium. It is reflecting into the same medium. It's called total internal reflection. Internally, it is totally reflecting into the same medium. It's called total internal reflection. Okay, the name itself suggesting bhaiya. Dekho bhaiya, all of you, students, please concentrate for 2 minutes of time. I will explain you this with medium 1. So, this is called as medium 1. Refractive index is N1. Medium 2. Refractive index is N2. Okay. This is the light incident. Please focus. Line drawn exactly perpendicular to that point of intersection is called as, what is the name? Very good, normal. All of you, I think all of you got that one, normal. Okay, right, bhaiya, dekho. If N1 is equal to N2, this will move straightly. If N1 is greater than N2, it will move away from the normal. If N1 is less than N2, it move towards the normal. Clear na? Very good bhaiya. If your theta 2 is equal to 90 degrees, dekho bhaiya, 90 degrees, then obviously the angle of incidence is called as theta c, critical angle. Clear bhaiya? Critical angle. Am I clear na? Theta 2 is equal to 90 degrees is called critical angle, theta c, and this is what called as your incident ray. Please focus. Is called as the incident ray. Is called as incident ray. Bhaiya. Whenever the light is incidenting, please observe the color, yellow color. Whenever the light is incidenting with an angle greater than theta c, clear na? Whenever the light is incidenting with an angle greater than theta c. See, light incidence is theta 1 bhaiya. When the light is incidenting with an angle greater than theta c, then it is called as light will be reflected into the same medium, and that angle is said to be called as theta 3. This light ray is called as reflected ray, and the angle maintained by the reflected ray is called as theta 3. Theta 1 is called as angle of incidence, theta 2 is called as angle of refraction, theta 3 is called as angle of reflection. I hope many students will study about the same thing in the electromagnetic wave theory also, EM theory, when you are talking about the reflection and refraction and reflection coefficients and refraction coefficients we are having. Same concept Bhaiya, there is no change, but here in terms of your permittivity and permeability, we are writing it as a refractive index N1 and N2. Hope it is clear for everyone in the class, and I think it is much easier for you to understand the case. I am writing here, just observe here, I am writing here. Whenever your theta 1 is greater than or worst case equal to theta c, that is the angle of incidence is greater than this critical angle, then what happened is the ray will be reflected back into the same medium, then theta 3 will become equal to theta 1. Your theta 3 will become equal to theta 1, that means your angle of incidence and angle of reflection becomes same, which is said to be called as total internal reflection. This is the principle that is used in the optical communication system. In optical communication system, we use the same principle Bhaiya. Whenever the light is passing into optical fiber cable, it has to take a total internal reflection and light will move in this way. How it happens in optical fiber cable, we will see in the topic in the tomorrow's class. While coming for the tomorrow's class, you must be study about all these reviews of optic topics and come to the class. Why? Because means we will study about that light passing through a fiber structure. इसमें कैसा है light from one end to another end कैसा move करेंगे और कैसा pass करेंगे, इसी concept के लिए ये पूरा basics चाहिए. ये पूरा बेसिक्स के हमको +2 में भी पढ़ा दिया, मैं ऑप्टिक्स पार्ट में पढ़ा दिया वो पूरा बेसिक्स. अभी तो हम पूरा बेसिक्स के लिए हमारा ऑप्टिकल कम्युनिकेशन में यूज़ करेंगे. इस ऑप्टिकल कम्युनिकेशन में कैसा यूज़ करेंगे, कैसा पास करेंगे लाइट और कैसा कैलकुलेट करेंगे मोड्स, वो पूरा इसी सब्जेक्ट में ले जाएंगे. देखना भैया. हाँ राइट. लिसन 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 लिसन. डोंट थिंक क्लास इज कंप्लीट भैया. 2 minutes. जस्ट फोकस. सर व्हाट हैपेंस? You talk about the case 1, that is theta 1 is greater than or equal to theta c, and you tell that theta 3 is equal to theta 1. Sir, what happened if light is incident with an angle less than theta c? देखो भैया, this is the incident light ray. See another light ray incident with an angle less than, see the theta 1 right now, see the theta 1 is right now less than theta c. Your theta 1 is less than theta c. Followed Nana? Theta 1 is less than theta c. Followed Nana? Very good. So, everybody in the class followed this. When theta 1 is less than theta c, whenever theta 1 is less than theta c, what happened is the light ray will refracted rather than reflection. Coming into the same medium is called reflection, but moving into the another medium is called as refraction, but it moves into the another medium, it's called refraction. The light ray is getting refracted. See, this is called which ray bhaiya? Refracted ray. But refracted ray depend upon the two cases, moving from rarer to denser or denser to rarer. Assumption, pure assumption bhaiya. What is the assumption that you are taking? Your N1 is greater than N2, means light ray is moving away from the normal. So, because light ray is moving from denser to rarer medium, so theta 2 is also greater than theta 1. Light ray moves away from normal, I hope everybody in the class understood this. And this is called as theta 2 bhaiya. This angle is called as theta 2 we are having. Is it clear? Refracted ray will be happens. So, when the total internal reflection will happens? Total internal reflections will be happen when incidence ray theta 1 is greater than or equal to theta c. If this condition is satisfies, then TIR will takes place, then theta 3 is equal to theta 1 is the concept of total internal reflection. If you understand this concept, in the tomorrow's class what happens is, we will explain to you in the class such that how light is moving from one medium to another medium. Today one student also asked a doubt, sir, how you know N1 and N2, which one is greater? Even I gave an example of water and air example to satisfy the constraint, but in the fiber you understand that very clearly. Why? Because means fiber manufacturing process, fiber is done, what is the inside the fiber we are having, all those things we will see. Then you understand clearly such that, okay, fiber is manufacturing with glass, so glass refractive index is N is equal to 1.5 in between 1.9. You take it as reference as 1.5, so that will going to be make an much impact on the values. So hope everybody in the class understood this. It is called as total internal reflection Bhaiya. I will tell you the point as a note to you. So you can please copy this part. Because of the time constraint, I am discussing about this note in the tomorrow's class. So you are also listening continuously the class from afternoon to this time, of course. So you can have a break. Tomorrow's class I can definitely explain you about the note of the TIR concept, and I can start explaining you about the refraction. Okay, how the light is passing, acceptance angle, numerical aperture, refractive index differences, relative refractive index differences. So tomorrow's class we will see about the things. Class starts by sharp 6 o'clock to 10 o'clock. You can expect a break in between 8 to 8:30. Maximum I can give a break at 8 o'clock only, 15 minutes break Bhaiya. Please stick to the timings, and if you have any doubts you can feel free to ask it. Telegram group also we have a group, you can put your doubts in that, I can explain to you there. But while coming for the tomorrow's class, please be prepared with the concept of review of optics and come to the class. So we see the remaining topics in the next class. Okay, dear students, good night. Okay, so Jai Hind. If you have any doubts, you can ask none. If you have any doubts, you can ask in the chat also, I can explain to you. Yeah, Vishwa Trivedi, tomorrow's class we will see about the core and cladding. I can explain about that core and cladding also. Vishwa, you already have the group now for EC and IN, online students batch 2024 batch. Telegram में group है ना? We always discuss about the timings, what are the class timings, what happening that one. Yeah, AR Singh, it is true. Your complete electromagnetic spectrum will behave as a our message signal, carrier to the message signal completely. Because all your message signals are at a low frequency, voice frequency range only, and all your carrier signals are in terms of kilohertz, megahertz, and with higher frequencies of carriers are present. Anuj Naik, if you take incident ray less than little less to 90, you asked, incident ray will be always be greater than or equal to the theta c, nana. It's not about 90. Means if you take little less of 90, then automatically what happened means it will leads to the reflected ray only. That's true only by taking like that. You are most welcome, Vishwa. Most welcome. Yeah, definitely I will show the radiant flux slide. Patel, I will show you the radiant flux slide to you. What is written P divided by in P of dB? That is power in terms of dB, P divided by 1 watt, nana. 1 watt. 1 watt in the sense means what is the unit of power divided by 1 watt. Reference is given with respect to 1 watt or reference with respect to power. Sure. Actually, carrier signal, there is not mandatory such that it always requires a channel for propagation. ARCing is not required always a channel to have a propagation. Need special type of channel for propagation, not like that. Whatever the channels we are having, those channels will carry these signals. Okay. If you want to tell about optical means, you require an optical cable. If it is other than other signals, we can transmit through the remaining cables also, like OFC, like power lines, or like a copper coaxial, and your waveguide also. Okay.